Hi everyone, welcome back to Chem Help ASAP. In this video, we are going to learn about the weakest of the intermolecular forces, London dispersion forces. However, don't be fooled. Just because they happen to be the weakest intermolecular force does not mean they do not have influence. We are going to see how the size and shape of molecules greatly affect physical properties. The first thing I want to do is I want to define intermolecular forces. And these are the attractive and repulsive forces that occur between molecules. Now, intermolecular forces can affect a variety of physical properties. Melting point, boiling point, vapor pressure, viscosity. These are just some of the properties that can be affected by intermolecular forces. The intermolecular force that I am focusing in on for this video are the London dispersion forces. Now, sometimes you'll see these called van der Waals forces or induced dipole forces. We're all talking about the same thing here. Now, these are the attractive and repulsive forces that occur between neutral nonpolar molecules. The key here is nonpolar molecules, so we want to keep that in mind. So let's take a look at a neutral nonpolar molecule. We're going to choose one of the simplest. Let's do a helium atom. Helium has two electrons that are orbiting the nucleus in the 1s orbital. And what can happen at some point in time is that, let's say, both of these electrons end up on this side of the molecule. What this does is this causes the right side of the molecule to have a partial negative charge because both electrons happen to be spending time over there. Therefore, the left side ends up with a partial positive charge. This is simply a spontaneous dipole. However, it has an effect on other helium atoms that are close to this one that had the spontaneous dipole. So if I put another helium atom right here close to this first one, the electrons on this right-hand side, this partial negative charge, are going to force the electrons on this second helium atom away, so they are also going to end up spending more time on the right-hand side. So again, we have a partial negative charge and a partial positive charge. We call this an induced dipole. Our first helium atom has caused our second helium atom to form a dipole. Now, what happens between these helium atoms? We set up a weak attraction between these two atoms. This is the London dispersion force. So you can imagine this does not just occur between two atoms, but any helium atoms that happen to be around. So this is why London dispersion forces are often also called induced dipole forces. Now, the size of the atom and how many electrons it has affects how polarizable it is. Helium is a pretty small atom, so if we maybe drew the helium atom a little smaller here, what if we were to say look at the xenon atom in comparison to the helium atom? Xenon is much larger, has many more electrons. So if xenon at some point ended up with all the electrons on the right-hand side, you could imagine that its partial negative and partial positive charge would be stronger than the helium. The way to test this is to look at one of the physical properties that's influenced by intermolecular forces and see if there is a trend. So let's take a look at some boiling points. Here is a table of the noble gases and their boiling points in degrees Celsius. I started with helium and I just ordered the noble gases in terms of size and number of electrons. Notice what happens with the boiling points. The boiling point of helium is negative 269 degrees C. But once we get up to radon, which is a much larger and much more polarizable atom, you'll notice that the boiling point has increased to negative 62 degrees C. It is actually much, much higher than helium. This is because the attractive forces in radon, even though they're still just induced dipole, are much stronger than what you find in helium. Let's look at the trend for hydrocarbons. So in my table here, I have several different hydrocarbons. Just for reference, a hydrocarbon is a molecule with only carbon and hydrogen. The black spheres here are my carbon atoms. The white spheres are my hydrogen atoms. So I started up here with methane. Its melting point is negative 183 degrees Celsius. What happens as I make this carbon chain longer and longer? So if I move from 1 carbon in methane to 2 carbons in ethane, my melting point goes up. And as I continue to add carbons all the way down here to octane, which has 8 carbons, my melting points continually increase. So the question is, of course, why? Well, these are all neutral, nonpolar molecules. They're all experiencing these induced dipole, London dispersion forces. The reason the melting points increase as you increase the number of carbons in the carbon chain is because not only does the surface area of the molecule increase, but the area of contact between them increase. So if I were to represent ethane as, say, a hot dog shape like this, here is the surface area of contact between them. But what about octane? Octane would be like a foot-long hot dog. And you would have a much greater surface area of contact between the molecules. That means it sets up greater attractive forces between these longer molecules, and therefore the melting points increase. But it is not only the size of the molecule that matters, the shape of the molecule can also affect how much this induced dipole intermolecular force can change physical properties. We will take a look at 3 structural isomers. All of these isomers have 5 carbon atoms and 12 hydrogen atoms. All that's different between them is how the atoms are bonded. So in my top molecule, I have 5 carbon atoms in a row. In my second molecule, you'll notice I put one of these carbon atoms coming off of the chain. And in my last isomer, you can see I have 1 central carbon with the other 4 carbons all bonded to it. How does the boiling point change with the shape of the molecule? You can see the boiling points go down the more I move away from this straight chain option up here. So let's see what's going on between the molecules. Here is a picture of multiple straight chain 5 carbon molecules. And you can see that they stack up pretty nicely. There is lots of area of contact between them. So there is a lot of induced dipole interaction happening between all of these molecules. What happens when we go to our first branched option? Here is a picture of our branched 5-carbon molecule, and you can see there's not quite as much interaction. We still have some good contact here, but it's not nearly as much as our straight chains. Now let's take a look at our most branched option, and you can see while there is still some contact here, it's really quite small, and the surface area of that contact is certainly greatly diminished from when we just had our straight chain molecule. So as you have fewer opportunities for those induced dipoles to interact and set up that attractive force, the boiling point goes down. This is another topic where I find my molecular modeling kit is really helpful. However, you can still do a quick internet search on just about any molecule and find some kind of 3D structure. Now, in our next video, we are going to see what happens when you have polar molecules. So I hope you'll join me for that. Thanks so much for watching.